what I was going to do today is just give you a brief overview of the kinds of things that I cover in 1606, which is a class that you would take as a junior in the fall semester. And so there's hundreds and hundreds of slides associated with that topic. There's about 10 here. And so we're just going to cover the basics of just sort of what you would try to do in a control class, the kinds of topics we cover. And then I've asked one of my students, Mark Cutler here, he's one of the grad students in my group, to come in and we'll show some things at the end actually flying around. So this will be two segments. First one just talking about the kinds of questions you would ask or be asked in that class. And then the second one will be sort of talking about where you might go from here, thinking specifically about these. So this is actually a prototype of an experiment we're building for 1606. The hope, if we get it done correctly, is that every one of you in that class would have one of these and you'd be doing control experiments on it as the semester goes on. So let's talk a little bit about what's involved. So this is automatic control, a little bit of motivation, control system overview, and block diagrams. So I brought in my trusty paper airplane. Built one of these things. This is a kind of cool way of doing it. This is a very specialized piece of cardboard that they give to you, and then you cut it out. You glue it all together and you get this. So it's a sophisticated looking paper airplane, and then of course I was throwing it with my daughter in a small room and it keeps whacking stuff. But if you've ever played paper airplanes, right, the first thing you do is you spend a lot of time building the thing, then you throw it, right, and what happens, right? Well, there's a sense of where you'd like it to go, right? So I'm gonna throw it, I'd like it to go over there, but of course it does something like that, right? So what I wanted was something that's straight, right, and it didn't necessarily fly in the direction I wanted to go. So what do? You walk over here, pick it up, right? And then hopefully nothing broke off, right? And if it did, you have to glue it back on. But the next thing you do, of course, you start fiddling with it, right? And what do you fiddle with? All the things on it, right? Well, once on here, right, you got the wings, and then you can bend them at the back, right? You got the tail, right? You can sort of bend them up or down to get sort of more either up or down motion. And then, of course, you got the rudder, which can help the thing turn. So the thing looked like it was sort of diving off to the right. So maybe we start fiddling in a certain way that'll give us a certain amount of lift and we'll sort of bend this wing down. And if we're lucky, right, no idea if this is going to work, right, it should now go in the opposite direction. Let's see what happens, right? Nope. Okay, right? So it shows how much I know about aerodynamics, right? It's been a long time since I took an aerodynamics class, maybe too long. Anyway, the point is that that's the closed loop process of doing control, right? Not very sophisticated, right? But I have some sense, hopefully I remember something about aerodynamics, right? It's been a while, maybe 20 years, but I've taken aerodynamics classes, right? And there's lots of flow theory and things like that about so on. But what I do know is that if I bend this wing down, it'll have a certain influence on how much lift this wing creates. And if it's sort of dropping off, then maybe I should try to get the thing to tilt back. So I have a mental model of how the dynamics of this, what the dynamics of the airplane are, okay? Most people that paint paper airplanes probably don't sit there and think about aerodynamics. They're just thinking about, that didn't work right, you know, let's just torque around. But over time, right, you will learn that model, right? If I do something, maybe I'll see a behavior and it'll be doing what I want now, maybe it won't, okay? It's not a very sophisticated control, but it's still control, right? So I have an error. The error is the difference between what I wanted and what I got, right? I visually saw that. I have a mental model of what's going on in my head in terms of the aerodynamics, and I then get to do something about it, right? I can actually torque the thing around and actually hopefully try to get it to fly in a better fashion, okay? So that's feedback control. It's just not a very high bandwidth feedback control, right? And if you want to get higher bandwidth feedback control, then you have to start putting something in which gives you a little more authority over that. Part of the problem here is, right, we have actuation, right, which I can bend the wings and do things to it. I can take the elevator, but I can't do anything once I release it, right? Once I throw it, it's gone. And until I pick it back up again and release it again, there's no loop that I can close. Now, if you get an airplane like this and you were sitting in the pilot seat, right, then of course, hopefully there's a stick in there. And what you can then do as a pilot is start using these other devices on here. These are the actuators, right? There's ailerons, there's flaps. Don't tend to use the flaps much in flight for high bandwidth stuff. But the ailerons, right, are the way that you would actually generate more lift in one wing or the other, and you can make the airplane do this, okay? That's your actuation capability on these current planes. And almost, you know, it's shown like this, but almost every airplane of the type that Elbridge is showing has almost the exact same set of things. And you'll look out the wing of an airplane, you'll see the ailerons moving all the time. There's the high-speed ones, there's the inboard of the I guess the low speed and the outboard of the high speed. But you've also got the rudders back here for sort of typically left-right, and elevators obviously for up-down. And of course, there's the engine, right? The big actuator at the front, which is the one we used to go fast, right? Okay? So I don't personally fly, but you know, if you were in that airplane, you would be the controller, right? When you're sitting in a car, you're the control system. I'm driving along, I look out the window, I see stuff that's going on, stuff I like, stuff I don't, I'm driving the car, okay? I'm the control system, you're in the airplane, you're the control system. What you then have to develop, again, is a mental model of what's going on in terms of the aerodynamics, what my actuation does, right? What's the other piece that we need to figure out in the airplane what's going on, right? How do we close the loop in the airplane, right? What's the other piece you need? Right, you know the dynamics? You know what the influence of moving the stick around does, or the yoke, right? So you like to know where it's going, right? Right? And you have to sense what it's going to be doing, okay? And how do you sense what it's doing, right? Well, you've got all kinds of things in your head that help you figure out where you're going. It helps you stand up, right? You can look out the window. You can see, well, there's the road. I'm following the road, right? And you might do that in an airplane. You might do that in a car, okay? So you need a sensor, okay? So the system, when we think about it, has dynamics, right? There's x dot equals, f of x. So you go off and learn, you'll take 1607 and learn all about this box in here. In our class, in 1606, we think about the system that looks like this. There's actuators, right? These are the things you can physically do to the system. In this object here, right? The actuators are the propellers, okay? There's the dynamics, which is the thing sort of moves around like this. And there's some, Newton had something to say about the dynamics, but then there's also the aerodynamics, okay? Those show up in here. And then there's the sensors, which, Mark is cleverly embedded on the board that's sitting in the middle here. In this case, you would have all kinds of things that would sit there, right? And what are the kinds of sensors you want for an aircraft, right? Well, if you're building anything, right, the first thing you do is put on GPS, right? If you're going to be outside, right? Gives you great information about position, velocity, as long as you can see the satellites, okay? You put gyros, those are the kinds of things that tell you angle rate. It means how you're turning like this or turning like that, okay? So that helps you figure out where you're pointing. You can also, if you have a compass, you can start thinking about where you're heading, right? If you're out hiking, you take a compass with you, so if you're on an airplane, you probably need one of those as well, okay? Where am I headed? And then a camera, if you're trying to look out the window and figure out what else is doing, it'd be good to have a camera, right? So certainly if you're building like an automated car, this is basically, that's where you start. And in fact, you're building automated anything, this is where you start. You just buy the stuff, stick it on there, and off you go. This has all that on there. It doesn't have GPS, right? It has the gyros, it has a compass, something that looks like a compass. You can put things like accelerometers on there, which will measure how the thing's accelerating. Those tend to be relatively crummy. We don't use them a whole lot, okay? So you take those sensors, slap them on the device. This is where you tend to spend a lot of money, by the way. There's a lot of money invested in this kind of stuff right here, certainly in the cameras and the GPS. But they sit up in this box here and they generate this signal we call Y. It's the stuff that's coming out, okay? You generate that whole thing, and then you put a big red box around the whole thing and call that G, okay? Now this could be linear, it could be nonlinear, it could be really anything. And depending on how sophisticated it is, you have to do different types of things. So Jeff was wondering how many classes we take. Well, the more classes you take, the more sophisticated version of G you can handle. You take 1606, G is gonna be pretty simple. You go off and take some nonlinear controls class in your sort of second year grad, G can be ugly, nonlinear, all kinds of weirdo things, okay? But we don't typically do that at the very beginning. It gets hard, okay? So this is the system. The question is, what's the control problem, right? So this is what we call, by the way, a block diagram, right? So it has, the sensors, the actuators, and now the red thing is G. The very basic control is just open loop. And what it can do is basically just, the straightforward strategy is just what we'll call plan inversion. So if this is G, the thing I just created that was in that red box, that basically what we're trying to do here is we have this reference command, which is the thing we would like, right? So in my case, that might have been the thing where we were thinking about, I want to fly in a dead straight line and hit the wall over there by the red blob, okay? That's the reference. What I saw come out was what it actually did, and what I'm going to try to generate is a controller here that basically just makes sure that this signal here looks like this signal here, okay? And so typically the goal is to make the output here, this Y, look like the reference. That's a sort of standard strategy. And one approach is just to make this look a lot like G inverse. Okay? And so the idea that if you take G inverse and multiply it by G, this is called plan inversion, very sophisticated name. But basically all it does is make the product of this times this equal 1. Okay? You can try that as a strategy. The problem is it doesn't work very well, okay? Which is why we have a whole class that then follows. And in fact, what we don't, you could try to do that, but instead you're better off doing this, okay? And this is the feedback strategy that says, okay, well, hold on a second, let's measure what Y looks like. And if Y doesn't look like R, which it probably isn't, okay, it's gonna look like R, and there's gonna be lots of reasons why it doesn't, then you difference those two and create this thing called E, the error. And what you do is you feed that back. So this is a feedback of the error through the control, and you use that control box in here, and this is what the entire class is about, to figure out what that signal U should be and then shove that into the system, okay? And the point is that this control here doesn't need to look like G inverse. It can be something quite different than that, and it'll be a whole lot better. This is a really bad idea and does not work, okay? It looks like a reasonable strategy on paper. It doesn't work in real life. In a nutshell, that's what you could try to do in the open loop, or you could try to do the closed. Now, just moving forward, and this is a brief analysis of, and it's really the only sort of analysis that's in these slides, of why would you use feedback or sort of feed-forward versus feedback, and sort of what's the comparison of the two. And what it tries to show here is that, for instance, if your system, and then I talked about G being quite sophisticated, right? So G could be sophisticated, but it could also be very simple. And in this case, I've just made it 10, okay? Which is the simplest, about as simple as a system you could probably imagine. It simply consists of the number 10. So you put in 1, you get out 10. You put in 2, you get out 20. It's just a multiplier, okay? And so the planned inversion that I created, this thing here, if this is 10, I just created an inversion, which is 1 over 10, okay? And so now when I stick a reference in right here in this top box up here, I stick in a number R, it goes through 1/10, it gets multiplied by 10, and then becomes Y, and of course Y looks exactly like R, right? And that was my goal. I wanted Y and R to look the same. It looks like a fantastic strategy. It should work. The closed loop approach, on the other hand, has this block diagram, right? This feedback loop. There's the plant again, it's 10. And rather arbitrarily, I introduced this number 5 here. This is actually my controller. It's different than the 10, right? The 1/10 that I had above, but I just introduced the number 5, okay? Now, if you went off and did the analysis, and again, these are the kinds of things we do in the class, they can actually show you how to compute the ratio Y over R, right? This one down here. And in open loop, as we said before, it's 1/10 of it multiplied by 10, which is 1, exactly the number I wanted to get. And in closed loop, when I do it, right, I actually, and you can work through the math, but it turns out that it's 50 over 51, which is really close to 1, but not 1, right? It's 0.9804, okay? So if you thought about this as well, it's like you said you wanted Y over R to be 1, and now you're proposing this feedback strategy which actually gets the answer 0.98. Isn't that worse than the open loop? Why are you talking about it, okay? Well, the fact of the matter is that I told you that the plant was 10, but what I'm also going to tell you is that I rarely know what the plant dynamics are very accurately, okay? And so let's look and see what happens if the plant dynamics aren't actually 10, but are in fact 15, okay? And you repeat the exact same calculation, okay? So this is just a repeat of the numbers we had above, right? If before it was actually 10, then you get 1. But if it turned out that the answer was 15, right? The system dynamics are actually 15, you actually get 1.5, okay? And I wanted the number to be 1, but if it turns out in the open loop strategy, right, I've got 1/10 multiplied by 15, I get 1.5 as the ratio, which is really crummy, okay? Because it's nowhere near 1. And if I look at my closed loop strategy and see how it's working, right, here I get 50 over 51, and if it's 15, instead I get 75 over 76, which is actually even closer to 1 than I got before, okay? So this raises sort of the key point as to why we use feedback, okay, is the open loop is much more prone to modeling errors, which we almost always have because we almost never know what's going on, okay, very accurately. The open loop, in the nominal case, when you happen to guess exactly what the dynamics are correctly, it's going to work better, right? Because G times G inverse is actually the right answer, but in terms of the robustness, i.e. how well it works if you get the model wrong, the open loop is really crummy, okay? And so that's the issue of robustness and sensitivity, okay, which is one of the themes of control that runs through all these 5 or 6 classes we were talking about. Robustness and sensitivity are key issues. And as I say to the students that take the class, it isn't just whether or not you can design a controller, it's whether you can design a controller that's actually going to work, okay? And if it's not robust, it's not going to work in real life, and that's the key, okay? So those are the kinds of issues that have to be faced, is basically how to actually get the thing to be robust. But there's another one, which is that most of the times the vehicle dynamics aren't even stable, okay? And I show a picture here, it's an F-117, which at the time I think I borrowed this picture, it was a very advanced airplane. Of course, you might laugh now and think, you know, why does it look so flat, right? This was a stealth fighter that I think I've already decommissioned, so it gives you an indication when I created this picture. But it was hideously unstable. This thing was designed to be stealth. It wasn't designed to fly well, okay? And so in fact, it just didn't want to stay in the air. So unless you had feedback control actually on the airplane, it wouldn't even stay up in the air. This is another mission that I've been working on, or have been working on before, and it's actually a bunch of satellites in low Earth orbit. And one of the things you know about satellites that look at this weird looking shape because they wanted to put radars on them is they create a lot of drag and they just like to drift apart. And so that whole formation, you might put it up there and it looks like it's going to stay nicely together. It won't. It'll just drift apart. And so you have to apply feedback control to stabilize it, okay? So the key thing typically is a lot of the systems we deal with in aerospace are just unstable. They just don't behave particularly well if you just left them alone. And so, for instance, if you think about this quad rotor, right, this is actually quite an unstable beast. If I let this go, it's not going to do anything useful. If I try to throw it up in the air, it's not going to fly particularly well. Mark, I think, will show you this flying. It'll be fairly stable, although it might create some hair-raising moments, but we'll see how it goes. It's a fairly small room to be flying this in. But the other thing is typically aerospace is also sort of performance-driven, right? You know, if you're thinking about an airline, you might be thinking of performance in terms of cost. You're really trying to eke out the most you can for the amount that you're spending on fuel. But if you're thinking about a military application, you might be thinking of performance, right? Where you think about just how accurately can you get some object into some, garbage can sized bin located several thousand miles away, okay? Those might be the kinds of questions you're thinking about. A lot of this is performance driven. It's a high performance system. You're really trying to get the best performance you can. So you might, stabilizing is interesting. You want to get more than that. You want to push harder, okay? And as I've said, there's oftentimes plant variations we have to deal with, the fact that dynamics are different than we thought, and that furthermore, there's a lot of disturbances. So if you go out, you'll notice there's a lot of wind. If you ever tried to fly an airplane outside, you ever tried to do something like a paper airplane outside, you see a lot of wind disturbances and things like that you have to deal with. So these are all things that we have to take into account. So with that, I'm going to stop. The next segment's going to talk a little bit more detail about specifically what's involved in the actual control design. Maybe we'll stop here for now, and then we'll restart the next segment.